Hello everyone, my name is Sourav Garg and I'm going to present on the topic visual place recognition, in particular a fast, compact and highly scalable system achieved through sequence-based matching of overloaded representations. This work was supported by Australian Centre for Robotic Vision and QUT Centre for Robotics and also received funding from an AOARD grant. Visual place recognition is a way to achieve mobile robot localization by matching the current visual information with what the robot has seen before. For this, the images are typically converted into some sort of robust representation, and then by matching different places, robot can achieve high localization performance, but it has to be then traded off with low storage footprint and low compute time requirements because these robots are generally resource constrained. The aim of this research is to develop a visual place recognition solution which has all these characteristics. First of all, a low overall storage footprint for the reference map or the reference database. This is something which has not been explored much in the past. And then simultaneously have extremely fast retrieval. And then as the robot keeps on exploring the environment, the storage growth should be sublinear or close to sublinear. Then we want a real-time localization system which is capable of localizing within a very large database, let's say having 10 million images. In the literature, there exists a number of quantization and hashing techniques, but the main aim is to reduce the quantization error and computation time, but not necessarily the storage footprint. And this is done by using long quantization vectors, which give short inverted lists of matches through which the final match is selected. On the other hand, we have sequence-based matching systems, where additional sequential information is used to disambiguate very challenging perceptual data. But the enhanced performance comes at the cost of increased computation time. In this paper, we propose an alternative approach where we use shorter quantization vectors, which give longer lists of candidate matches. Now, this overloaded representation is then used along with sequence matching to disambiguate between different candidates. In particular, we invert the target criteria of existing quantization and hashing techniques and aim for much shorter quantization vectors, leading to longer lists of candidate matches, and then use sequence-based matching to disambiguate between different candidates and retrieve the final match. Our proposed approach, dubbed as coarse hash, converts the input image descriptors into a hash space. Now, this is done by using all the image descriptors from the reference database, which represents a reference map, into a low dimensional space first. This is achieved by running PCA. And then we do clustering per dimension of these descriptors. Given the output of PCA, it has mutually orthogonal axes, and all the different descriptor dimensions are decorrelated from each other. If we use 2 clusters per dimension, we get a binary label per descriptor dimension. So for a 12-dimensional descriptor, we have a 12-bit vector as an output. So this training is done on the reference database, but then any query descriptor, any query image can then be converted into this 12-bit vector. Now this 12-bit vector can be directly converted into a hash address. For example, we'll have 4096 hash addresses here. But because we use a large database, for example, in this case, we use 40,000 images. So for each hash address, we'll have multiple reference indices tagged to that address. For example, for hash address 1, we have around 10 different reference images tagged to it. Now, having this overloaded representation, we then use sequence matching on top to disambiguate between these different candidates and get the final match. Now, given a list of candidate matches per query descriptor, we can then look for matching sequences throughout the reference database. Now, we do not need to match a query with all the reference indices. We only consider those potential matches which have been retrieved for that particular hash address. So the green boxes here show those elements which have the same hash address, and the white boxes show those elements which are not considered for matching unless they fall into a line of sequence. And for them, we can compute some distance using Hamming space, but for the green boxes, the distance would be 0 as the hash address is the same. So considering a 3-frame sequence as shown in this example, we can then find a sequence score which is the lowest for the one dark green box shown here. and this is our final match. Most of the existing visual place recognition benchmarks are only limited to a few thousands of images. Now, in order to benchmark our proposed method on a very large scale dataset, we borrow the image retrieval dataset deep 1 billion, which has images which are unordered, which means adjacent images are not related to each other, which is not the case with localization datasets where we have sequential information inherent within such datasets. So we follow a series of steps to concatenate a real-world dataset, which is 40.100K, and the deep 1 billion dataset by using homogenization, which means we do a sliding window averaging on the deep 1 billion dataset. So there is some sequential information which is common across images which are adjacent. And then we do variance equalization so that there is no data bias for one particular ingredient dataset. And then finally, we create a query traverse out of the reference dataset by adding some noise, which has been generated using the real world dataset. So with this, we create three different datasets. One is 20,000, 20K, and then a 1 million and a 10 million dataset, which has images from deep 1 billion and some appended images at the end from the real world 4700K dataset. We compare our method against a baseline, which is a brute force matcher based on original descriptors without using any dimension reduction or hashing. Now, in order to compare the recall performance, we make sure that the computational budget is the same for both the methods. This includes the compute time requirements and the overall storage footprint. To achieve this, the baseline system has chopped down descriptor dimensions so that the storage footprint is matched, and a limited number of candidates being used for sequence matching so that the compute time requirements are matched. Line color represents in these plots different methods, and a dotted, dashed, and a solid line represents different sequence lengths used for place recognition. We can observe that there is a significant improvement in recall performance under the same computational budget and even for very small values of localization radii. A similar trend can be observed for the 1 million dataset, although the absolute performance has dropped from before because of the size of the dataset. And then we can also observe that the same trend continues for the 10 million dataset, where using a sequence length of 50 or 100, we can retrieve some matches in a 10 million size database, whereas the baseline is unable to provide any good results. One of the key parameters of our proposed system is the length of the vector. So as we keep on reducing the length of the vector, we retrieve a longer list of candidates, which means more collisions. And this also means that the sequence matching will have to do more work. This increases the computation time, but it also increases the performance. So there is this trade-off between computation time and performance, but there is no much change in the storage footprint. With similar settings for the baseline system, even increasing these candidates to a very large number, it does not really show any good performance. Here we show the storage growth for our proposed system. There are a few different elements that are stored for the reference database, which represents a reference map. So the main component is the reference index to hash address map, meaning for every reference index, there is a hash address stored. And then there are three different components which only depend on the descriptor dimensions. One is cluster centers, other is PCA transformation matrix, and PCA mean descriptor. But overall storage footprint for all these different datasets is very low. For example, for the 10 million dataset, we only need 80.4 MB of storage space. These are some of the qualitative results. For the 4700K dataset, where we do have access to the real world images, we show that we could retrieve 98 correct matches out of 267 queries within a 1 million sized reference database, whereas the brute force matcher could only retrieve just one match. We found that by effectively combining quantization and hashing techniques and sequence-based matching, which is well suited to large-scale place recognition and localization tasks, one can achieve high performance while simultaneously having a low overall storage footprint and very low compute time requirements. If you have any suggestions or queries, please feel free to contact at the email address provided. For more details on how the dataset was generated, some scripts are provided at the GitHub page, for which this QR code and link is provided here. Thank you.